now move on to parameter estimation. So parameter estimation is just determining the optimal values of the parameters using the data that we collected and under the assumption that the structure of the model is known. So basically what we say is that the mathematical model is exactly known. There is no uncertainty about the model, but only uncertainty in the data. So we will look for the unknown parameters that will give me the best fit of the model based on the data that we have, but assuming that my model is exactly correct. So we will be using an objective function to reach this goal. An objective function is just a measure for the distance between the model prediction and the experimental data. So it's measuring the distance between my observations on the one hand, so the yi, and my model predictions yi hat. The easiest measure is the Euclidean distance, so it's just looking at how different are they. So I take the difference between my prediction and my observation, which corresponds to epsilon I. What we will do extra here is we will denote theta, so we will say explicitly that my prediction depends on theta, because later on we will have different values of theta when we have iterative processes. So we minimize the total distance. So what we do is we look at the differences between the observations and the predictions, and we sum over all the observations. Similar as to linear regression, just summing is not good, because a number of those distances are positive, a number of the distances are negative, and in the end if you just sum them you will get 0. So we take again a squared sum of distances, so yi minus yi hat, you sum them over all of the observations, capital N, and then you get your objective function. So the objective function is denoted by capital J, and it is the objective function depending on the parameters theta. So we will minimize this objective function over theta. If we want to extend to multiple variables, it's easy to do. So multiple variables basically is we have multiple equations or multiple outputs. So assume we have a first output that we are interested in y1, which is alpha plus beta times x1, and you have a second one y2, which is let's say gamma plus delta times x1 plus psi times x2. If we want to minimize, we have to minimize over the set of equations. So we have to minimize over both equations simultaneously. It's very important to realize that minimizing over a set of equations at the same time is not necessarily the same as minimizing over each of the equations separately. As soon as there are parameters which are appearing in one or in two or more equations, so they reappear in other equations, then it's not the same. So if this zeta, for example, would have been the same beta as in the first equation, then you cannot minimize them separately, but you have to minimize them simultaneously. How to do this is basically summing them up. It's very easy. It's a very straightforward solution. So you minimize over the first one. So you minimize with respect to my first variable, my first output. You look at the differences between predictions and the observations. You sum them and so on and so on. And then you do the same for the second, the third, and so on. And then you just add them. So you put them all in the same objective function. So when you minimize your objective function, you minimize over all of them at the same time. So just adding them, summing them up, minimizes or makes sure that your objective function looks at all of them at the same time. And then minimizing the objective function is the same as simultaneously minimizing all of the different equations. In the first part, so we have assumed that they have a similar variance. So each of them, or basically each equation has a variation as a variance, depending on the stochasticity of the variable. So I have an x1 in my first, I have x2 and an x1 in the second one. So they are all uncertain. There is a certain uncertainty in my y1, y2, and so on. Because of the variables, they are linked to a probability density function, so they carry on this uncertainty in the output. So we have an output with a certain uncertainty, so with a certain band around it. If all of those bands are approximately the same thing, it doesn't really matter to incorporate this in my equation, in my objective function. If there are different variances, then we have to do this. So basically this corresponds to different measurement errors. So each of the outputs, so the output variables, has a different measurement error. So y1 has a measurement error or a variance corresponding to sigma 1 squared, y2 has sigma 2 squared, and so on. So what we then do is we have to incorporate this uncertainty, this variation in the objective function. How do we incorporate? We divide. So you divide each sum of squares by the variance. Why would we divide by the variance? Because if my variance is small, this becomes a very large term, which means that here, let's say sigma 1 squared small, which means that 1 divided by sigma 1 squared is big, which means that this term is always large in my equation. So it means that it gets a lot of weight in the equation. If I then want to minimize my objective function, I want to find a minimal value for this objective function, this will be large no matter what I do. So it will put more focus on the other term, for example, and it will try to get these fits as close as possible to each other. So it will try to get these distances as small as possible, because anyway my first term is large. So if I have a small variance, I give it a large weight, because with a small variance I am always pretty certain of the output that I get. So no matter what values of the parameters I use, it will have very little influence on my prediction. So here, no matter of the values of my parameters, this prediction will always be very close to this observation. And so it doesn't really matter to get these very accurately, but I want to have the parameters with a lot of variation. I want to estimate those accurately, because then I can say, look, I have found parameters such that all my outputs are very close, or all of my predictions are very close to my observations. And so if we want to write this in the matrix notation, we can do it in the following way. Why do we use matrix notations? Because it's often more easy to solve them manually through matrix notations, but also a lot of programs work on matrix computation, such as MATLAB. So MATLAB basically, behind the scenes, works with matrices to solve everything. So what you get is, you get a yi minus y hat I, which is just the vector of all the differences. So yi minus y hat I is y1i minus y hat 1i. So it is, for my first output, the difference between the ith observation and the ith prediction, and so on. So this one is for variable y1 observation I. And then the qi is for this observation, just the diagonal matrix with all of the inverse variances. So if you work this out, then you see that this is exactly the same as the second objective function. So what we do here is we minimize j theta over the values of theta, the possible values of theta, in such a way that my predictions and my observations are as close as possible together.